is ME407 Mechatronics, part 7 of the module 1. In this part we will be discussing about different types of solenoid valves. Then we will be discussing on resolvers and synchros. Then we will be dealing with the different types of acoustic emission sensors. Solenoid. Solenoid is a electromagnetic actuator. Is what showing a solenoid basic working. It consists of a movable ferrite core, is what it is showing in the center. A movable ferrite core can move in the either direction. That is activated by the current flowing through that. When the coil is energized, a magnetic field is established that provides the force to push or pull the coil. So, when this coil is, we are going to energize, and the current is flowing through this ferrite core, a push or pull force is created. The peculiarity is a large force over a short duration is possible with this solenoid valve. We can exert a large force for a duration is very short. Direct acting two-way solenoid valve. It is, the figure shows the cross-sectional view of a two-way solenoid valve, direct acting type. So the flow direction is from here to here. You can see this pink color tree shows that a coil winding. This coil will be, if you want to open this valve, you have to energize this coil. Normally it will be in a closed condition, it will be in a de-energized condition. So what happens in a de-energized condition? Valve will be in a closed condition. How the flow is coming from here, fluid pressure will be coming from here and exerting a force here, and this valve will be closed. And there is no flow happening through this valve. Once this coil is energized, you will be lifting this spool against the spring force, and this valve will be open and flow can happen through this direction. So this is how the working is. So when energized, the core and seal are pulled into a solenoid coil and the valve opens. The electromagnetic force is greater than the combined spring force, and the static and dynamic pressure force of the medium. Against this fluid pressure, this valve is opened. This is a schematic of the working of direct acting two-way solenoid valve. Exam point of view, I think this will be better for you to reproduce. Same what I explained in the previous slide. The working is, flow is from, in this direction from A to F. Normally it is a closed position against the spring force. It is not working, and this is what you are energizing coil. Here it is in an open condition to show it. It is energized, so it is lifting this valve against the spring force and the fluid pressure, and flow is happening through here. This is open condition. This is the closed. Before going to the photo cells, the basic principle on which these photo cells are working, photoconductive principle. Light increases the flow of electrons and reduces the resistance. Photovoltaic principle is, light makes electrons to move between layers, producing a voltage and a current in the external circuit. Photoemissive, light knocks the electron from a cathode to an anode, making a current flow through an external circuit. This is what some basic three principles on which photo cells are working. Photoemissive cell, the principle is, these photo devices are light sensitive material like calcium that releases the free electron when struck by the photons of sufficient energy. The energy of the photons depending upon the frequency of the light. High frequency light greater is the energy of the photons which converts the light energy into electrical energy. This electrical energy, if you are monitoring, you can say how much is the light that is falling on that. This is what is a cathode. On that light is falling, it will be producing a electron that will be connected by the anode. That is what it is shown here in this figure. And this how much electron is falling can be make a voltage difference that we can monitor. Photoconductive cells. The principle is these photoconductive cells, when exposed to light, their electrical resistance varies. So this is what it is shown here. In a substrate we have got a thin strip of photoresistive material enclosed. So its resistance varies when the light falls on that. This is what it is represented here. Depending upon the light falling, the resistances keep on changing. Here you can see the luminous light intensity, the resistance of the material. Here the photoresistive material changes. That resistance change, if you are going to monitor, you can measure what is the light intensity. Now it comes to another topic called resolver. Resolver is used to measure the angular position. For example, in a machine tool, the lead screw position. Previously, you have discussed about the rotary encoder, where you can measure the angular position. Same way, resolver also you can use for measuring the angular position. The resolver consists of a stator and rotor winding. It is having a stator and rotor winding. Two windings, stator and rotor. It is mounted at 90 degree apart. That is what it is schematically represented. It is 90 degree apart. So we sin phi for this winding, we cos phi for this winding. So two windings in a 90 degree phase shift. So the working of the resolver is, in a resolver, the output signal is as a function of the rotation is obtained by inductive coupling between the stator and rotor. If an AC voltage is applied to one of the stator coil, a maximum voltage will appear at the rotor coil. When these two coils are in line, and the voltage will disappear for plus or minus 90 degree shift. This angular position change, there is a change in the voltage. It will vary from maximum to minimum depending upon the two coil positions. When the shaft is rotated, the induced voltage in one rotor coil follows a sine curve and the voltage induced in the other follows a cosine curve. So the phase angle phi depends on the angular position of the rotor shaft. So this we can use it. This principle can be used for measuring the position of the rotor. Hence, for example, if the rotor is rotated 90 degree, the output voltage of the rotor winding is shifted by 90 electrical degrees. Synchros. In function, the synchro is a electromechanical transducer. It's a transducer. This is what schematic of a synchro is shown. It has got three windings, three stator winding, 1, 2 and 3 at 120 degree apart phase shift. We have got a rotor winding. A mechanical input such as a shaft rotation is converted to a unique set of output voltage. Whatever rotation is happening to the rotor, there is a output voltage is generated, or in other ways, Using some particular input voltage, you can achieve a required rotation also. This is what it is saying here. A set of input voltage is used to turn a synchro motor to a desired position. So I repeat again. A mechanical input such as a shaft rotation is converted to a unique set of output voltage. Either you can measure as an output voltage, or giving input as a voltage, you can position the motor to a required position also. That is what? A set of input voltage is used to turn the synchro motor to a desired position. The complete circle represents the rotor. The solid bars represent the cause of the winding next to them. Power to the rotor is connected by slip rings and brushes. This is a construction arrangement. The rotor induces equal voltage in the 120 degree, 240 degree winding and no voltage in the zero windings. And does not necessarily needed to be connected to a common lead of the stator star winding.
This milling machine has several axes driven by a servo motion system. Actually, as a feedback sensor, there is a resolver installed. But how is this resolver working? After this video, you will have a better idea. The resolver consists of a stationary part called stator and a revolving part called rotor, which is attached to the motor shaft. The primary winding of the stator is connected to a high-frequency sine signal. This sine signal is transmitted to the rotor winding because the stator's primary winding and the rotor winding act together, like a transformer. Furthermore, we can name the rotor winding also as reference winding. The relative magnitudes of the sine and cosine voltage are measured to determine the angle of the rotor relative to the stator. To get an output signal, we have two secondary stator windings, a so-called sine and a cosine winding, which are displaced angularly to each other by 90 degrees. So, let's mount this resolver to the motor shaft and apply a high-frequency sine signal to the stator primary winding. The pulsating alternating magnetic field of the rotor winding now induces an alternating voltage in the measuring windings sine and cosine. Their amplitudes, however, depend on the angular position of the rotor. If the rotor winding and the measuring winding are parallel to one another, the magnetic rotor field completely passes through the measuring coil. Therefore, the induced voltage is maximum. And at 0 degree shaft angle, the cosine wave also has its maximum. If the rotor winding and measuring winding are at a right angle to each other, no voltage is induced. Let's turn the motor shaft 90 degrees, and we can prove all these statements. So, let's change the time base of our oscilloscope and watch the measuring signals. What you see now is that you get a modulated sine and a cosine measuring signal, which are also called envelope curve. It's now up to the resolver digital converter, RDC, to evaluate the current rotor position and the rotational speed from these signal curves. Well, unlike encoders, resolvers have no electronic components, and therefore robust against soiling, vibrations, and work safely even within a wide temperature range. This makes them highly reliable and environmentally resistant. Watch also our next videos.
Piezoelectric sensor. It is a measuring device that uses the piezoelectric effect to measure the change in pressure, temperature, acceleration, strain or force by converting them to an electrical energy. This is following circuit shows the how a schematic diagram of a piezoelectric sensor working. Basic principle of piezoelectric sensor is piezo effect or piezoelectric effect is the ability of a certain material to generate an electric charge in response to the applied mechanical stress. It actually came from a Greek word piezein, which means squeeze or press, and piezo is a Greek word for push. This is a schematic diagram shows a force is applied in a piezo material. There is an electrode to check the voltage what it is generated. So by applying the force, material, piezo material is changing its shape, it will generate a voltage. So here it is showing another diagram how this piezo material is pressed between two electrodes and how we are monitoring the voltage. Laser Doppler vibrometer, LDV. It is a non-contact type vibration measuring instrument. A laser beam from LDV is directed on the surface of interest. The vibration amplitude and frequency can be extracted from Doppler shift of the reflected laser beam frequency due to the motion of the surface. Here it is showing this is a target or moving object and laser beam is directed towards this, and there are two beam splitters in between, and once the main beam is split here and go this way, again another beam splitter it will take a route of here. So laser beam that is falling on the target will be reflected from here and you are finding out a detection. So what is the Doppler shift between a moving object and this is your reference beam. So this is one reference beam and another beam after going to the object it is coming back and coming here. What is the shift happening because of the moving object that you can measure using this photo detector? This is what the working of a laser Doppler vibrometer. Acoustic emission sensor. What is acoustic emission? Acoustic emission or AE is the phenomena of radiation of acoustic or elastic waves in solids that occurs when a material undergoes irreversible changes in its internal structure, for example, as a result of crack formation or plastic deformation or due to aging, temperature gradient or external mechanical forces. A is occurring during the process of mechanical loading of the materials and structures that is accompanied by the structural change that generate the local source of elastic waves. This is a schematic of acoustic emission sensor working. This is how it looks in a physical form. It is having this material you want to test where there is a crack. So a stress wave is created here by applying a force or stress in this direction that is sensed through the sensor, and there is an amplification. This acquisition system will store this information and you are getting through a software you are getting a display. The same thing it is represented schematically. This is the material you are applying a stress using sensor. This is the sensor, it is coming here, you are monitoring it, and signal amplification, then you are measuring. Main components of AE instrumentation are sensor used to detect the AE event, preamplifier amplifies the initial signal, cable for transfer of signal a distance up to 200 meter. Then comes the data acquisition device which performs the filtration, signals, parameter evaluation, data analysis and charting. This is a schematic diagram: sensor, preamplifier, main amplifier, measuring and a computer system and software. There is a wide application for the AE sensors. It includes inspection of manufacturing products, monitoring of safety of structures, and the development of the new material. This acoustic emission is a sound emitted as an elastic wave by a solid when it is deformed or struck. The use of AE sensors to detect these elastic waves and to non-destructively test on the material is called as the AE method. So we can check a structure or a system before the failure is happening by picking up the trend in AE. AE methods can detect what is the flaws that is happening in a structure or a material. The typical non-destructive testing methods are ultrasonic testing, radiographic testing, eddy current testing, acoustic emission testing. This is the physical how looks like the sensors looks like. Different types of AE sensors are there. Basically two types: resonance model or narrow band model that are highly sensitive at a high specific frequency. Another model is wide bandwidth model that possesses a constant sensitivity across a wide band of frequency. Depending upon the classification, either of this model will be selected. First one, resonance model. This is one schematic of the resonance model. It is having a connector, case and a piezo ceramic material here and a wear plate that is also made of ceramic. How it works? The mechanical resonance of the detector element is used to obtain high sensitivity. Generally, this type of sensors have a resonance frequency in the range of 60 kHz to 1 MHz. These AE sensors, this piezoelectric ceramic wire is AE sensors having a piezoelectric accelerometer design are used if a lower resonance characteristics are required. Second one, wide bandwidth model. The schematic is shown here. So damper is there and a piece of ceramic is here. So here, compared to the previous model, here a damper is also bonded. A damper is bonded on the top of the detector element to suppress the resonance. This is to avoid the resonance. So then some of the application of AE sensors are AE sensors can pick up warning signals from manufactured products that human sense cannot detect. AE sensors have a wide range of applications from quality control, inspection of manufactured goods to safety inspection of large structures.